Hello and Assalamualaikum warahmatullahi wabarakatuh. We are from Section 5, Mechanics of Material, Group 13. We'll present our group's project, which is fiber reinforced bar versus steel bars. Before we start our presentation, I am Nurul Azahra Abdul Jamal.
I am Umi Safuha binti Sidi.
I'm Amni Mahira binti Muhammad Hashim.
And I am Hamizah binti Zainil.
Fiber reinforcement polymer have shown significant promise and have indeed been used in hundreds of field applications around the world as either external confining reinforcement or as internal reinforcement for structure members. Fiber reinforcement polymer bars also used in lieu of steels as a reinforcing material in concrete members to extend the service life of constructed facilities because of its better resistance to corrosion and higher damping properties than steel. Fiber reinforcement polymer bars also can be result in lower maintenance costs by eliminating corrosion-induced damage. Longitudinal internal reinforcement play an important role in resisting the tensile stresses, improving the buckling resistance, and increasing the fracture capacity of the column. Besides, a rebar or reinforcing bar is a common steel bar and is generally used in reinforced concrete structures. Mild steel rebars are the most common as its price is relatively low while it provides material properties that are acceptable for many applications. The objective of this research are: first, to determine if fiber reinforced bar or steel reinforced bar are desirable substitute for construction. Second, determine the strength of fiber reinforced bar and steel reinforced bar. Third, determine the ultimate load capacity of reinforced. Next, determine the yield strength. Determine the modulus of elasticity. Determine the tensile modulus of elasticity. Determine the ultimate tensile strength. And the last one is determine the ultimate strain.
There are several types of reinforced fiber bars and steel bars. The first type of fiber bar reinforcement is glass fiber reinforced polymer (GFRP), which is glass fibers are basically made by mixing silica sand, limestone, folic acid, and other minor ingredients. The mix is heated until it melts at about 1260 degrees Celsius. The molten glass is then allowed to flow through fine holes in a platinum plate. The glass strands are cooled, gathered, and wound. The fibers are drawn to increase directional strength. The fibers are then woven into various forms for use in composites. Based on an aluminum-lime borosilicate composition, glass-produced fibers are considered as the predominant reinforcement for polymer-metric composites due to their high electrical insulating properties, low susceptibility to moisture, and high mechanical properties. Glass is generally a good impact-resistant fiber, but weighs more than carbon or aramide. Glass fibers are excellent characteristics, equal to or better than steel in certain forms. The second one is carbon fiber reinforced polymer (CFRP), which is carbon fibers have a high modulus of elasticity, which is 200 until 800 GPa, and then the ultimate elongation is 0.3 until 2.5%, where the lower elongation corresponds to the higher stiffness and vice versa. Carbon fibers do not absorb water and are resistant to many chemical solutions. They withstand fatigue excellently and neither corrode nor show any creep or relaxation. Furthermore, there are also have two types of steel bar. The first one is hot rolled deformed bars. which is hot rolled deformed bars are mostly commonly used steel reinforcement for RCC structures. As the name says, the hot rolling of the reinforcement is undergone leaving certain deformations on its surface in the form of ribs. These ribs help to form a bond with the concrete. The typical yield strength of hot rolled deformed bars is 60,000 psi, and the second one is mild steel plain bars, which is the mild steel plain reinforcement bars do not have ribs on their surface. They have a plain surface. These bars are used for small projects where the major concern is the economy. The tensile yield strength of these bars has a value of 40,000 psi. For the background study, this research was to investigate whether a fiber reinforced polymer (FRP) rebar has satisfactory properties to be used as primary reinforcement within concrete structures. This was done by testing bond strength, which is axial pull-out, flexural strength, and final load in terms of toughness, and comparing it to a steel bar specimen of the same length and nominal diameter. Carbon, glass, and aramide are three major types of fibers which are used in construction. The composite is often named by the reinforcing fiber, for instance, CFRP for carbon fiber reinforced polymer. Besides that, steel reinforcement bars are used within concrete due to their high performance with regards to strength, coefficiency, and wide availability. A rebar or reinforcing bar is a common steel bar and is generally used in reinforced concrete structures. In this study, we discussed about the properties of steel and the fiber bar reinforcement. We also just focus part of slenderness ratio in type of longitudinal reinforcement, steel or CFRP. For test parameter only, we discuss more about the things that are related with the internal reinforcement, which is steel and CFRP bars, which reinforce CFFT columns, such are the compressive strength, yield strength, ultimate strength, and load strength. Next is for the test specimens and parameter. 12 circular concrete columns were tested under pure axial compression loading during the study case. The test parameter for the concrete column named as internal reinforcement experiment. The materials of steel or carbon fiber reinforced polymer (CFRP) bars are used to reinforce the columns. Deformed steel bars number 10 m or number 30 m, which are nominal diameter of 9.52 and 12.7 respectively, were used as longitudinal reinforcement in RC and CFFT columns. The next material used for this experiment was sand-coated CFRP bars, which nominal diameter of 9.52 mm. CFRP bars was used for the FRP reinforced CFFT columns as longitudinal reinforcement for this study. All of the column specimens in this study were constructed from one type of concrete strength. The concrete strength of all the specimens has been set with 30 MPa as its target strength. Concrete batch was supplied by ready-mix concrete supplier. The maximum size of the coarse aggregates was about 20 mm. 5 plain concrete cylinders 152,305 mm were prepared and cured under the same conditions as the tested specimens. 5 cylinders were tested in compression after 28 days. The 28 days average concrete compressive strength was found equal to 30 plus minus 0.6 MPa.
So, the test result of properties of reinforcing steel bars and CFRP bars are presented in Table 1 and 2, which consists of nominal area mm squared, yield strength megapascal, ultimate strength megapascal, and modulus of elasticity gigapascal. Table 3 and Figure 1 shows the result due to the test of the specimen. The result test specimen included the result of control specimen, steel reinforced CFFT columns and carbon FRP reinforced CFFT columns. The identification control was used to present the control specimen, while identification S and C refer to the type of the internal reinforcement, steel and CFRP bars respectively. In the figure 1, series number 1 present the RC control specimen with steel type. Series number 2, 3 and 4 present CFFT columns that were reinforced internally with 6 steel bars and 6 CFRP bars. Okay, we proceed with the instrumentation and test setup for steel and CFRP bars reinforced CFFT column. The first test is local strain distribution test. The local strain distribution of the specimen was captured by the internal and external instrumentation in this study. Two of the longitudinal steel or CFRP bars with 180 apart were installed with the strain gauges at the mid-height before casting. Before testing, two axial and two hoop electrical resistant strain gauges were mounted 180 apart along the hoop direction on the external surface of the specimens. At the quarter height level for the 1200 mm and 1500 mm height specimen, two pairs of the strain gauges were added and also mounted. Strain distribution from steel CFRP bars and concrete were obtained using the value of 6 mm length of strain gauges. Figure 2 shows the overview of the test setup for the instrumentation layout. The next test is specimen test. The axial and the horizontal displacement for each column were measured by two linear variable displacement transducer LVDT 180 apart along the hoop direction of the specimen. A thin layer of the high strength sulfur capping was prepared on the top and the bottom surfaces before the test to ensure the uniform stress distribution during the test. Two circular steel tie wraps of 4 mm thickness and 16 mm width were used to confine the two ends of the loading for each specimen, and it's also used to avoid the local failure of the specimen above and below the test regions. The bars in all CFFT specimens were fixed using two steel stirrup of 3.2 mm diameter at the distance of 25 mm from the top and the bottom of the height. To fix the bars during casting, additional steel spiral was added at the mid-height of the 1500 mm height specimen. By using funny machine that have 6000 kN capacity, the specimen were tested where the columns were set up vertically at the center of the loading plates of the machine. The specimen were tested represented the case of fixed column due to the fact that the upper and lower clamp of the testing machine were prevented from rotation. So, figure 3 shows the reinforcement cages for the steel specimen which used for the test, while figure 4 shows the schematic view of the apparatus for the test, and figure 5 shows the laboratory setup during the test. So we move to the experimental test result. The result test shows in terms of the failure modes, ultimate load capacity, deformation characteristic, and stress-strain relationship of the control and reinforced CFFT columns, terms of the yield and ultimate loads, and the failure mechanism. From this table, the confined concrete compressive strength FCC prime megapascal, the maximum compressive strength just before failure, and the effectiveness of the confining technique FCX prime per FC prime, and also the failure mode result for all the specimens tested were presented. Based on the table 4, the column with slenderness ratio 8, 12 and 14 have the failure modes were a combination of concrete compression failure, C, rupture, R of the confining, FRP tubes, and local buckling, L of the internal reinforcing bar at the column mid-height. It is of interest to mention that for specimen with slenderness ratio less or equal to 14, the CFFT columns buckle just before the rupture of the tube. So these are the failure mode for all the specimen. The failure in the two control specimen was dominant by crushing of concrete. The figure 7 and 8 shows the different failure modes for steel and CFRP reinforced CFFT columns. From the figure we can see that there have the different height between the steel and CFRP reinforced CFFT columns cause of the failure test.
Next is analysis data. The load strain response of longitudinal steel and CFRP reinforcements in the graph obtained presents the relationship between the axial load on the columns and axial strain in the steel of CFRP longitudinal bars of the tested specimens. For steel reinforcement CFFT columns, which is 14S2, 14S3, the load strain curve exhibited a linear response until yielding of the steel bars, which occurred a strain approximately equal to 0.002 mm per millimeter. The unconfined concrete compressive strength achieved after the steel bars started to yield close. The load bar strain for CFRP bars from the graph shows that in the initial stage of the curve, a linear response occurred till reaching a strain of 0.002, followed by a gradual semi-linear response increasing till the peak load. It should be noted that the CFRP bars did not exhibit a yield point. Instead, a linear elastic response controls the specimen till failure. For the conclusion, we can conclude that the steel bars are better than the CFRP reinforced bars in terms of their compressive strength, the load bar strain, the load axial deformation. Next, the test result indicates that the axial capacity of CFRP reinforced CFFT result in 13%, 7%, 5%, and 0% reduction as compared to steel reinforced CFFT columns. The axial compressive strength of the steel and CFRP reinforced CFFT's column was reduced approximately by 32% and 22% respectively, with increasing the slenderness ratio from 8 to 20. And the last one is the test results indicate that the axial capacity of CFRP reinforced CFFT results in 13%, 7%, 5%, and 0% reduction as compared to steel reinforced CFFT columns that had slenderness ratio 8, 12, 16, and 20 respectively. So that's all from us. Thank you.